Okay, so the next section is all about inverse functions. So if you don't know what these are, that's okay. We're about to introduce them now. But you actually know about inverses whether you think you do or not. In other words, you've been dealing with inverse operations for a long time. Like in your pre-algebra, in like junior high math, what did you learn would undo addition? Subtraction undoes addition, right? What undoes or cancels out division? Multiplication, right? What cancels out a squared power? Square rooting both sides, right? All of those things are inverses, okay? So inverse functions are just two opposite functions that kind of undo each other, much like those examples I just gave you. It's just that instead of operations, they're going to be functions. So this is not the definition you would find in the book, but it is what happens, okay? They end up kind of canceling each other out when using composition of functions. But another way to think about inverse functions is they are the functions we get when we swap x and y. So another way to think of inverses are all the x's become y's and all the y's become x's. All right, so before we get to the steps for finding inverses, which we're about to, I want to make a couple statements. First of all, not all functions have inverses at all. Okay, and I'm going to teach you how to recognize when one wouldn't have one. And so one way to recognize if a function is going to have an inverse is a visual test. Now, we already have a vertical line test to tell whether something's a function. So if we have a special kind of function called a one-to-one function, or another way to say that is it passes the vertical line test. The horizontal line test. So what was the vertical line test? How many times was a vertical line only supposed to be able to hit the graph if it was a function? Only once. So I'm not going to make a big thing about defining the horizontal line test. It just means that a horizontal line only crosses the graph once. Okay, but only functions that pass this horizontal line test on top of the vertical line test will have an inverse. All right, so we're going to look at an example in a minute, but if you're pretty sure that the function has an inverse, here is how you find it. So I like to do steps for things so that later on you can go back and look, and if you've forgotten what we did in class, if you're doing your homework, then you have kind of some procedures to follow. So the first thing is you're going to replace f of x with y. So if you have f of x equals something, you'll change it to y. Okay, and then you're going to swap x and y. Okay, so don't make that harder than it is. It means just like you would think. If it's an x, change it to a y. If it's a y, change it to an x. Okay, and then step number 2 is make the new equation look like y equals. Okay, so we like our equations to look like y equals. And then the last step is really just an observation. If the new equation is a function, then that's your answer. Okay, so in other words, if the answer you get seems legitimate, then it's your answer, it's your inverse. But if it is not a function, then it doesn't necessarily mean you did something wrong. It just means that the original doesn't have one to begin with. So I'm going to say then the original function has no inverse. So in other words, you did your process, you did what you were supposed to do, and you got something weird. It means that there was no answer to begin with. But by the way, it also means that that original graph must have failed the horizontal line test. So in other words, if you can graph your functions or at least sketch an idea of what the shape is, then you may not even have to go through the trouble of trying to find an inverse just for you to find out that there wasn't one. Okay, so let's find an inverse if it exists. Okay. So find the inverse of y equals 4x. So before we start, you might want to at least think about what the graph looks like. Okay? So maybe over off to the side, let's sketch what the graph is. What kind of equation or picture does 4x give us? I want you to know just by looking for the test upcoming next week. It's a line, right? So I don't even need details. I know that it's a line. Okay, and so what do we notice about this line? Does it pass the horizontal line test? Yes. Okay, so I'm just going to say passes horizontal line test. All that tells us is we're good to go ahead. Okay, we're good to go ahead and find what the inverse is. So notice we have a y equals equation. So the inverse of that is going to be what? What are we going to do with x and y? Flip them, right, or swap them. So it's going to be x equals 4y. But then I need this new equation to look like proper form, right? So what do I want the new equation to look like? Y equals, so I'm just going to divide both sides by 4. Okay, so notice we get y equals x over 4. Notice that that is a function. So that means y equals 4x and y equals x divided by 4 are what to each other? Inverses. Okay. By the way, notice that like we switched the operation, right? What operation were we doing originally? Like 4 and x are being what to each other? Multiplied, right? And then what did we switch it to for the inverse function? To the opposite of multiplication, which is what? Division, right? The x divided by 4 is the opposite. Okay, so that's kind of why it works that way. All right, so let's do another one. So let's look at find the inverse of f of x equals x squared. Okay, so kind of like we did the last one, let's sketch the graph. And again, I expect you to know what that graph looks like in general, right? What kind of graphs are x squared graphs? Parabolas, right? So when you look at the graph, notice that it does not pass the horizontal line test, right? It actually fails the horizontal line test. Okay, so what does that mean for us then? It means there's no inverse. Okay, so if you think about what the graph is, there's no need to proceed. However, I almost always have students that like fly through it and don't want to think about the graph. Okay, so we're going to call this method A. And it's definitely the preferred method because we were able to come up with that in like 5 seconds, right? Okay, but here is what you're going to have to do if you don't notice that. So let's say you don't pay attention to the graph and you just try to barrel through it. Okay, well then you're going to first replace f of x with y, right? And then you're going to attempt to find the inverse by doing what with x and y? With inverse, we always do what with x and y? Swap them, right? So what will the new equation look like? X equals what? Y squared, right? Instead of y equals x squared, it's the opposite. X equals y squared. But then if I want to solve this for y, I need to take the what of both sides? The square root. But notice when I do, and you might have forgotten that you're supposed to do that, but you have to include the plus or minus, okay? So you end up getting y equals plus or minus the square root of x, okay, which is not a function. And the reason it's not a function is because you would repeat your x's. In other words, like, let's take an example, for instance. If x was 1, x equals 1 would be paired up with two different answers, both positive 1 and negative 1. Okay, so we would have a repeat of the x values, and we're not allowed to have that. Okay, so at any rate, this still doesn't have an inverse. But which one's clearly easier, method A or method B? Method A is definitely easier. Okay, so try to think about the graph before you just haul off and start the problem. Okay, it'll make your life a whole lot easier. Okay, so let's look at one more, and then we're going to introduce some notation. So find the inverse of g of x equals 2x plus 3. Okay, so the first thing is, without graphing it, I'm just going to make this note. Note that it passes the horizontal line test. How do you know that?
Oh, it's a line.
It's a line, yeah.
So will we have calculators though, like on the test? Or
You are allowed to use a calculator on the test. Okay. But again, these are graphs from, remember when we did the common graphs? Like, those are things you're going to have to know for the test anyway. So, but yes, you will be allowed to use the calculator. All right, so it doesn't mean we're finished. We just know that we can proceed, right? Like, we know it's there's a point in doing it, basically. So first, remember, we're going to rewrite this as y equals 2x plus 3. And then we're going to do what with x and y? Swap them. So it's going to be x equals 2y plus 3. So I just need to clean up that function. In other words, I need to make this look like what? All functions, when we can, we want to make them look like what equals? Y equals, right? So we need to first maybe move the 3. So I'm going to subtract 3 from both sides. So that's going to give me x minus 3 equals 2y. And then I need to divide by what? 2. So I get y equals x minus 3 over 2. Okay, this is my inverse function of the original. Okay, so I'm about to introduce some notation, but notice, like, the opposite operations are occurring. Okay, so what two operations are happening here where I'm pointing? We're multiplying the 2 times the x, and we're doing what after that? Adding, right? So we're multiplying and adding. Notice what operations we're doing instead on the inverse. Instead of multiplying and adding, we're doing what? Subtraction and division, right? So you can kind of figure that out usually. Okay, you just need to know kind of what order to go in. Okay, so we do have some notation for inverse. In other words, we don't always just write out the word inverse. So this is what it looks like, and I don't want you to get confused with our function notation. If you want the inverse of a function f of x, then the notation for that is this right here, okay? And that's not an exponent. This literally means the inverse of f of x. So when you see a -1 that looks like it's in the exponent spot, it's not an exponent. It's just trying to tell you that those are inverses. So for example 3 above, we can say that f of x was 2x plus 3, and the inverse of that was what? X minus 3 over 2. Okay, so rather than having to write the word inverse out, we can use this notation that means the same thing. It means inverse. So let's do one that I think is a little more of a challenge. I'm going to put a star by this example, which I don't really do very much. I don't put stars by actual example numbers, but I'm letting you know that I probably plan on putting a question like this on the test. Okay, so this is the one I really want you to pay the most attention to. So it says if f of x equals 2x plus 1 over x minus 3, then I want you to find what? What am I asking you to find? What's that notation mean? Yes, it means inverse. Okay. Now this is a graph we don't know very well, but if you plug this in the calculator, it does pass the horizontal line test. Okay, so all that tells us is we're not going to waste our time, right? We can move along. Okay, so let's look at what the inverse equation would be. So the first thing is, if you want to, you can replace this with y, so that you can swap them, right? So what will the new inverse equation look like to start off with then? Instead of y equals, it'll be what? X equals, and it'll be 2y plus 1 over y minus 3. Okay? If that was all we had to do with inverses, those would be really relatively simple, right? But we have to make the equation look like what when we're done? Y equals, and that's going to be more of a challenge because it's in a fraction form. Okay, so I would assume that most of us don't really like fractions, so we're going to get it out of fraction form as soon as we can. Okay, so in other words, I'm going to put that over 1 and I'm going to cross multiply. If you have a fraction equal to another fraction, you can always cross multiply and then you won't be dealing with a fraction anymore. Okay, so let's do that. So x times that denominator, so make sure you use parentheses. So it's x minus, or x times y minus 3 equals 1 times that numerator. Okay, so anytime you have a fraction equal to another fraction, you're allowed to cross multiply. So now let's just distributive property on both sides. Although on the right side, multiplying by 1 is not going to do much, right? So we're going to get xy minus 3x and then equals 2y plus 1. Okay, so what's our goal again at this point? We want to make this look like what when we're done? Y equals. The problem that you might notice is like which y, right? There are 2 of them, okay? So when there are 2 of them, you want to group them together. So what I mean by that is we need to pull this one to this side so that they are together. And then I'm also going to move the non-y thing over to this side. Okay, so don't overthink that. These are going away, right? So then what would be on the left when I shift things around that way? xy minus 2y, right? What about on the right? 3x plus 1. Okay, so I want to get y all by itself, so right now I'm just getting both of them by themselves. But then notice that if I wanted to simplify this, what do you notice both of these have in common? They each have a what in them? A y, so I'm going to pull or factor it out, and that would leave me with x minus 2. Notice I didn't do anything to the right. So we're actually like almost finished. We're almost there. Okay, we just said, hey, this has a y and so does this, so I'm going to divide it out. But now notice I've got y times something, okay? And I don't really want that something there, right? I want to isolate or get y all alone. So what's the opposite of multiplying something? Division, right? So if I want to get rid of something, I just have to make sure I do the same thing to both sides. Right? And why is that helpful? Because what am I going to be able to do here? Get rid of it there, right? And so in the end, I just get y equals 3x plus 1 over x minus 2. So if we use our new notation, then our inverse equation was 3x plus 1 over x minus 2. Okay, so you're going to have an opportunity on your homework to practice that one, and I would just say pay particular attention to that one because I'm letting you know I'm probably going to ask you a question like that on the test. Yes?
Why is negative 2 instead of defining?
You mean like?
Oh, you divided it.
Yeah. Oh, yeah, I divided it. That bar means I'm dividing. I'm not.
I just can't see the right.
Oh, yeah. Okay, by the way, notice, like, let's compare these two guys that I'm pointing at. Notice, like, I didn't get different numbers, they're just all spread around, right? Like, so you shouldn't get something, like, you shouldn't start with numbers like 1, 2, and 3 and end up with numbers like 47 and hence, or like, they'll all be similar, they'll just be shifted around and changed up a bit. Okay, so one more shorter one, and then I want to look at maybe what composition of functions has to do with this. So let's say I have h of x equals the cube root of x, and I ask you to find the inverse. So we just need to get used to this notation, meaning inverse. Okay, so this is one of our common graphs. So we can sketch this one if we want, okay? I don't know if you remember what cube root graphs look like, but they come up this way and they go this way, okay? But what do you notice about that curve if you know what it looks like? It passes the horizontal line test. Remember, it also passes the vertical line test if it's a function, but horizontal line test is what we use to determine if we're going to have an answer for inverse or not. Okay. So let's write out what since we know we have an answer, right? If it passes the horizontal line test, we have an answer. What will the inverse look like? Okay, remember, we're going to replace this with y, right? So what will the new inverse equation look like? X equals the cube root of y. Okay, so this one looks weird, but it's actually really not near as difficult as the one we just did, right? If I want to get y all by itself, I want to undo the cube root, right? What undoes cube root? Like, what can I do to this to undo that cube root? So can't I just, I don't know if that's what you said, but can't I just cube it, like raise it to the third power? Because cube root and cubing are opposites of each other, right? But whatever I do to one side, what do I have to make sure and remember? Do to the same to the other side, right? So we end up just getting y equals x cubed. In other words, the inverse equation for the original was just x cubed. That really shouldn't take you by surprise, because what is the opposite operation of cube rooting? Cubing, right? So like the answer to the inverse is always what's happening opposite operation-wise. Okay, so let's pull in what we just talked about from 2.6, because inverses and composition of functions have very much to do with each other. So if you have two functions, f and g, and we know they're inverses of each other, then a couple of things happen. The first thing is f of g of x and g of f of x are the same as each other. Okay, so remember how I said they wouldn't be the same unless it was a special case? This is the special case. And actually, they both equal x. In other words, they simplify and cancel each other out, until their most simple piece. Okay, so stay with me on this, because you're going to need to make sure that you show this in the right order. So let's see if we can show that 5x and x divided by 5, the functions, are inverses using this rule. Now, I certainly think it looks like they're going to be inverses. Why do you think I say that? Because what operation is happening here? Multiplication. What operations happen in here? Division, and that sounds right to me, right? Like those are opposites. Okay, so maybe it's going to work. But this is how you have to show it. You have to find f of g of x, and we're going to compare that with g of f of x. And we should get not only the same answer, but we should get plain old vanilla x, like nothing else going on with it, okay? So just like we did in the last section, let's remember where we start, right? So we're going to start in the inside. So f of g of x means replace g of x with what it is, right? So what is g of x? X over 5. Okay, but what does this mean? Now that means go plug that into f, right? So instead of 5x, I'm going to get 5 times x over 5. So if you want to, you can think of that as over 1. Okay, so notice what's going to happen to a 5 on top compared with a 5 on bottom. What's going to happen to my 5s? It's basically like 5 over 5, which is just what? 1. So these cancel out and you're left with only x. Okay, notice that was what was supposed to happen. We were supposed to get plain old x. In other words, everything else goes away, leaving only x. So let's try the other way. What's supposed to happen here just the same way? What are we supposed to end up with as a result? X again. That should be plain old x. Okay, but this time we're going to start here. So it's going to be g of 5x. Okay, so that means go look at your g equation and plug that in, right? So instead of x over 5, what am I going to have? 5x over 5. Notice it looks a bit different, but not much, okay? Because what's still going to get canceled? The 5s are going to get canceled, and we're going to end up with x. Okay? So notice, we got what we wanted in both places. So you don't have to do this for every problem, but I at least on the first one want you to explain it. So I got f of g of x, and I found g of f of x. And they were both equal to x. So that means f and g were inverses. So notice there's a whole lot that can go wrong with these, right? Like it's very, very specific. That's why I said it's only very special cases where you will get the same thing for both sides of composition of functions. Okay, so let me do one like I expect my math lab is probably going to throw at you. So the question is, are these two equations inverses of each other? So at first glance, I think we're pretty okay, maybe. Because notice that f of x is multiplying and subtracting, right? And g of x is adding and dividing. So it at least look like we're okay operations-wise. So how do we show they are inverses or not? We have to find both of these guys, right? We have to find f of g of x, and honestly, it's a good further practice of composition of functions anyway. So I need to find both of these, and what are they both supposed to be? X. Okay, so let's see what happens. So we're going to start on the inside, so it's going to be f of x plus 3 over 7. Probably not my favorite, right? I'm going to have to plug in a fraction. But that's okay. So we're going to get 3 times that thing, because I'm plugging this in for x, and then minus 7. So do you notice that things aren't quite where they should be, right? Like what would you really want this denominator to be if it was going to cancel with this 3? You wanted it to also be a 3, right? So it's not really turning out so great, okay? But for the My Math Lab question, they're going to want you to just go ahead and finish it out, okay? So in other words, we're going to go ahead and work on this and see, but I think we can kind of see ahead of time, hey, this doesn't look like it's going to work. So I'm going to distribute the 3. So this is going to be 3x plus 9 over 7 minus 7. So maybe still holding on some hope, but let's put that over 7, or over 1, I mean. Okay, because my math lab always wants simplified answers. So what do I want this denominator to be so that I have a common denominator? Remember, you're not allowed to add and subtract denominators that aren't the same, right? So what do I want this denominator to be then? 7, whatever I do to the bottom, I have to do the same to the top. So it's a little bit of pre-algebra review, right? So I get this minus 49 over 7. Okay. Why did I do that? Because now that they have a common denominator, I am allowed to combine them, right? So this is going to be, looks like 3x minus 40 over 7. So I don't want to spend a whole lot of time on fraction review, but you are going to need to know some basic math before you can jump into college algebra. But at any rate, what do we know? Like, this is clearly not x, right? Like, it is not as simple as we wanted it to be, okay? So we already know the answer is a big fat what? No, okay? But my math lab, to get the full question right, will want you to go ahead and go through on the other side. And like I said, it's just good pre-algebra practice anyway, okay? So I don't expect you to love that you have to do that, but just know that there's only like one question like this on the homework. So I'm going to do g of the inside, which is 3x minus 7. This way is actually easier. So what does this mean? Come up here, right, and stick this in. So we're going to get 3x minus 7 plus 3 over 7. So we still get a fraction, but at least we don't have to like combine two fractions together. So this is much more pleasant. It's 3x minus 4 over 7, but still doesn't equal what we wanted it to be. Okay. So for lots of reasons, what would we say about f and g then? They are not inverses, yes. Okay, so it's a very specific requirement for them to be inverses. They have to both be the same as each other, okay, and they have to equal perfectly plain old x. In other words, everything has to cancel each other out other than the x term. Okay, so one last thing about inverses, again, that can help you if you have a graph already, is that inverses are reflections of each other. Over the line y equals x. Okay, I'm putting a star by this because I want you to know it. Okay, so I'm going to show you a picture of it, but then we're going to talk about kind of what it means. Okay, so now I'm going to underline this. Okay, y equals x is like the simplest diagonal line we can have. Okay, so let's look at one where I'm going to ask you to maybe use different color writing utensils to graph so that we can really see the difference between them. But let's go for an axis that goes out 5. All right, so I'm going to list some points for you and we're going to connect them. So let's say that f of x consists of these points. 3, 5, 2, -1, and 0, -3. I'm having you write down the points so that your graph can match with mine. Okay, so 3, 5 is here, 2, -1 is here, and then 0, -3 is here, and I want you to connect them like this. So by the way, how come we know that's a function? It is one. What's the way that we tell if something's a function or not? Passes what test? Vertical line test. Okay, so while you're kind of graphing it, I want to ask you that. All right, so first, let's say that I asked you to graph what? What am I asking you to graph in words?
The inverse.
The inverse, yes. I'm asking you to graph the inverse. Okay, so first of all, before we graph it, let's draw the line y equals x so you know what I mean by it's the simplest diagonal you can have. In other words, it's a diagonal with a slope of 1. Like the m in front of x is 1. So it's just that perfect diagonal line that crosses through the center. So notice it's kind of hard to picture this being folded over this line, right? But what's going to happen to this chunk of it? It's going to go where? Like here, right? And then this is going to lay over here, right? So you might be able to eyeball and tell it, but I don't think you really have to if you remember what inverse means, right? What does inverse always mean? Yeah, just swap the x's and the y's, and you have actual numbers you can swap this time, right? So what will the 0.35 change to with the inverse function? 5.3. And then what will this point change to? -1, 2, right? And this one will be -3, 0. Notice that's a whole lot easier than trying to eyeball it, right? So this will be -5.3, which will be about here. My lines aren't perfect, but that's okay. So maybe about right here. -1, 2 will be here. And then -3, 0 will be here. So understanding that my line definitely isn't perfect, okay? Because actually, my diagonal line should have perfectly crossed it in the center here, which mine didn't do because my stuff wasn't spaced out perfectly. But I think you can see the general shape of it, right? So this would be considered the inverse graph. So it really doesn't matter whether you have equations or whether you have numbers in this case. What are we still doing with x and y? We're swapping them, either in x, using the letters to swap them, or in this case, we're swapping the numbers.